Hi, my name is Emmett Greenberg, and I will be presenting my project on predicting demand of a bike-sharing rental system. I obtained the dataset from Kaggle.com. It's for bike rentals in the Capital Bike Share system in Washington, D.C. The data contains the hourly and daily bike rental counts over a 2-year period from 2011 to 2012. Separately, it contains a breakdown of rental counts for both registered and unregistered or casual users. The dataset also contains information about weather and season. Independent variables include temperature, humidity, wind speed, day of week, and whether it's a holiday. Using these variables, I will predict the number of bikes rented in a given hour over a 2-year period. The bike share company needs to predict the number of bikes needed and where in order to maximize utility and customer satisfaction. Because there is no data available for the stations from which the bikes are rented, I will not be able to figure out the optimal locations, so I'll only be predicting the number of bikes needed in the system on an hourly basis over the 2-year duration. Based on my calculations, there should be 17,520 hours in this time frame, and the actual data contains slightly less than this, so there is a relatively small number of hours at which data was not recorded. I began my data exploration by plotting a correlation heat map between some of the variables, as shown here. The target variable is the count, CNT. This shows some very strong correlations with the target variable, such as with only the registered users. It shows a moderate positive correlation with temp and atemp, which is the feels like temperature. There is also a moderate negative correlation with humidity. I reduced the dimensionality by removing columns that were not useful, such as the index, and I converted the categorical variables into factors for better interpretability. I then plotted my dependent variable against various independent variables. In doing so, I found that season and weather situation had an effect on how many bikes were rented, as did the hour of the day. Additionally, I observed that the rentals increased substantially over the second year of the data. This plot shows the trends that occur in the number of rentals over each hour of the day, on average. Ridership spikes during peak commuting times, first around 8 in the morning, and then between 4 and 6 in the afternoon. This pattern holds even in the winter, just with lower totals across the whole day. After exploring the data and then becoming familiar with it, I moved to data transformation. The data was already normalized, and there were no missing values, so I randomly sampled and replaced some values in the temperature column with NA. I then imputed using the value from the previous observation, because hourly temperature is usually not that much different than that of the previous hour. Here is the code in which I am imputing missing values and then replacing the NAs. I also detected outliers using an interquartile range function, as shown here. This removed a total of 342 observations, which is only about 1% of the data. After splitting my data into training and testing, I then constructed 3 models: decision tree, Poisson regression, and linear regression. I chose a regression decision tree because I am predicting a continuous variable. Then I chose 2 regression models: Poisson because it is often used for modeling count data, and classic linear regression for comparison. For my regression decision tree, I used rpart. When I run my model, it produces the following output. Each node in the tree represents a decision point, and each final node a prediction. As this shows, the variables temperature and humidity were considered by this model to be the most important features for predicting rentals. My second model is a Poisson regression, and the output is shown below. My third model is a linear regression model, as shown with the following code. When comparing the results of these models, you see that none of them performed very well. The Model 1 performed a little bit better than the others, and Model 2 performed a little bit worse than Model 3. I did a k-fold cross-validation in which I resampled the data, k equals 10 times, and it resulted in similar results as shown below. For hyperparameter tuning, I varied the parameters min split, min bucket, and complexity, the CP parameter. I alternated complexity between 0.1, 0.01, and 0.001. The GLM and LM functions did not have hyperparameter tuning options, so I was not able to tune those parameters. Baseline results were an RMSE of 156.8 and an MAE of 116.8 when varying the various hyperparameters. The RMSE varied from 154.9 to 170.9, and the MAE varied from 114.8 to 130.6, and these numbers are not substantially different from the baseline model. As far as the regularization, for Model 1, some adjustment of model complexity was done in the hyperparameter tuning because I altered the complexity parameter. To further explore regularization for Model 1, I will alter the tree's depth. From my results, I found that regularization through control of max depth had no effect on the RMSE and MAE. I tried 2 attempts at creating an ensemble model. The first attempt is the function below, which attempts to find the average of the 3 predictions. The function ran, but when I tried to call the function with my testing data, it resulted in an error, and unfortunately I was not able to solve this. My second attempt uses the ensembler.regression function from the meta-ensemble-R package. However, here I ran into an error that I could not correct and was not able to solve it. There are 2 potential reasons for the performance of my model. First, I might have run the models incorrectly. I repeatedly checked my work and I'm getting the same results each time, so this appears to be less likely. It is also possible that something may be fundamentally wrong with the dataset, and the variables I chose are not good predictors of the number of bike rentals over the 2-year period. In support of the latter conclusion, there is a publication where the author constructed a similar approach using a linear regression model. They predicted daily bike rentals instead of hourly rentals and used temperature, wind speed, and humidity as predictor variable, whereas I used those variables plus the holiday variable. In that study, the author reported an R-squared value of 0.46. They did not report RMSE or MAE for direct comparison. Therefore, I created a scatter plot and my calculated R-squared value is 0.39. This is similar and supports the conclusion that these variables are poor predictors of the dataset. In further support of the poor predictive values of these chosen set of variables, Another study used these same variables plus an additional set of variables and obtained a much better result. In this study, the author used holiday, humidity, temperature, and wind speed, plus season, weekend versus non-weekend, and presence of rain and snow as other variables. Some of these variables were derived variables through categorization in the underlying data set, which I did not do. Using a linear model, the author reported a mean squared error of 0.0167, which indicates excellent model performance. This further supports the likelihood that the set of variables I selected for my model are not good predictors.